Welcome to lecture 32 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. In this lecture, our topic of discussion is defect states and carrier recombination. In last lecture, we have discussed band tail states in a disordered amorphous semiconductor material and also the near band edge absorption or absorption tail in a amorphous semiconductor material. In this lecture, we will focus on defect states, carrier recombination, minority carrier lifetime, etc. In last lecture, we have discussed and we have seen there is a extended states in the forbidden gap due to structural disorder and phonon induced disorder. In addition to these extended states, there are some defect states also, and these states are basically lying in the mid gap, that is near the middle, and the distribution of these states follow the Gaussian distribution, and these states arises due to defects in the material, maybe structural defects, not the disorder, some defects. Suppose one particular atom is missing, or in place of a particular atom, so different atom of different material is there, or some defects are there. Suppose some boron atoms and the silicon are there. So these states, which are basically lying in the middle side of the forbidden gap, they are assumed to be responsible mainly for recombination. So from the band tail states also recombination may take place, but the Gaussian distributed mid gap defect states are more prone to assist the trap assisted recombination, and these states are called defect states, and the recombination assisted by these states are called defect or trap assisted recombination, which is Shockley-Redhall recombination. We have already discussed in lecture 19. From the lecture 19, if we rewrite the recombination rate, we can write this: rate of recombination R is equal to Pn minus Ni square, with Pn greater than Ni square, because this is a non-equilibrium Pn greater than Ni square, and the states which I want to mean the Gaussian distributed. Gaussian distributed mid-gap states. Now the trap assisted recombination rate, already we derived this expression. This is Pn minus Ni square divided by, this is 1 by sigma p Vtp Nt, which is nothing but tau p. There is a lifetime of hole into n plus n1. What is n? N is the carrier concentration at non-equilibrium, which is nothing but n0 plus some delta n. n0 is the equilibrium and delta n is the extra carriers generated maybe due to elimination or due to other external energy. N1 is nothing but, if you see the expression of N1, this is nothing but carrier concentration or electron concentration in the trap state, Nt. And the second term in the denominator, which is 1 by sigma n Vtn Nt, that is tau n, electron lifetime. Tau p is the whole lifetime, tau n is the electron lifetime. P plus P1. P means whole concentration at non-equilibrium, which is again P0 plus delta P may be written, because P0 is the equilibrium concentration and delta P is the excess generated concentration of hole. And P1 is again is nothing but whole concentration at the trap state. How this P1 and N1 is basically expressing the carrier concentration at the trap state. Let us see. The N1, the expression what we have obtained or we derived in lecture 19, if we rewrite the N1, it is nothing but this. Suppose this is the N1 expression was N1. If you see the expression for N1, it was Nc exponential Et minus Ec by Kt, and Et is a trap energy state, Nc is the effective density of states in the conduction band, Ec is the conduction band H, Kt is a K is a Boltzmann constant, you know T is the temperature. If we consider room temperature, so Kt value will be 25.85 or 26 millivolt. Kt is milli electron volt, Kt by Q is millivolt. Anyway, now let us expand this expression of N1, Nc exponential Et minus Ec by Kt. So you multiply this and you rearrange the algebraically in this way. Suppose this is Et minus EFI by Kt into exponential EFI minus Ec by Kt. So exponential EFI by Kt and exponential minus EFI by Kt, this will be cancelled out. So ultimately you will get Ni exponential Et minus EFI into exponential EFI minus Ec by Kt. But we also know that Nc into exponential EFI minus Ec by Kt, this is nothing but the intrinsic carrier concentration, because we are considering the Fermi level in the intrinsic case. So EF is replaced by EFI. So here we have done some rearrangement by putting EFI, Et minus EFI into EFI minus Ec. So ultimately the result is Et minus Ec is coming. So Et minus EFI by Kt remains here, Et minus EFI by Kt, and Nc with this EFI minus EC by KT, this is nothing but Ni. This is equal to Ni. That is why it is written that Ni. Ni into exponential Et minus EFI by KT, and EFI also you can write in terms of EFI, you can express only simply EI. So Et minus EI, Ni exponential Et minus EI by KT, which is nothing but Nt. You can write this is a Nt. So N1 is nothing but Nt. So this is equal to Nt. That is equal to carrier concentration or electron concentration in the trap state. Similarly, Pt, P1 is equal to Pt. It can be written that similarly P1 is equal to Pt. There is a whole concentration at trap state. Trap state energy is Et. Now, in the lifetime of hole and electron, there are three terms, that is sigma p, Vtp, Nt, and this sigma n, Vtn, Nt in case of tau n. Sigma p is nothing but the capture cross section for holes. So we can write tau p is equal to 1 by sigma p Vtp into Nt, and tau n is equal to 1 by sigma n Vtn into Nt. Now what is the order of these values? The capture cross section, say sigma n, this is in the order of say 5 angstrom square. Angstrom square means that is equal to 5 into 10 to the power minus 8 into 10 to the power minus 8 centimeter square. And thermal velocity Vtn is equal to thermal velocity. This is in the order of 10 to the power 5 meter per second. And Nt, there is a density of trap states that is varying, say 10 to the power 14 to 10 to the power say 18 per centimeter cube. So by putting this value, you can get the tau value in the order of nanosecond or picosecond. Anyway, so let us take two examples to calculate the approximate value of recombination rate and minority carrier lifetime, because both are related. Recombination rate is inversely proportional to the carrier lifetime. So let us consider a n-type silicon with low level illumination. That means n-type silicon semiconductor is uniformly illuminated by light but at a low level illumination. So let us consider this. This is a n-type silicon. This is uniformly illuminated. So equilibrium carrier concentration was, that is before illumination, N0 and P0 are the concentration of electrons and holes respectively. After illumination, N will be N0 plus delta N, and P is equal to P0 plus delta P. Delta P and delta N are photo-generated excess holes and LHS carriers, excess electrons. So delta P is equal to delta N. But you remember, the low level illumination means the excess minority carrier which is generated, which is much less than the majority carrier concentration, equilibrium majority carrier concentration. That means the excess minority carrier, so low level illumination or injection, whatever you tell, illumination is more appropriate here. For low level illumination, excess minority carrier, that is excess minority hole here, that is less than the majority carrier N0. This is the condition for low level illumination. Now let us rewrite the expression for Shockley red hole recombination rate R. So what will be the R? R expression is equal to the top side Pn minus Ni square by tau P into N plus Nt plus tau N into P plus Pt. We can write P now P0 plus delta P into N is N0 plus delta N minus Ni square if Et is equal to Ei, say. Suppose the trap state is exactly at the middle, that is, it is coinciding with the intrinsic Fermi level, that is Ei. If Et is equal to Ei, so tau P N0 plus delta N plus Nt will be Ni. So Nt is nothing but Ni. Plus tau N P0 plus delta P plus Ni. Is equal to, say, P0 N0 plus N0 delta P plus P0 delta N plus delta P delta N minus Ni square by here N0 plus delta N, you see delta N and N0. Delta N is negligible compared to the N0 value. Also Ni is also less compared to N0 value. So N0 in the order of suppose 10 to the power 16, 17, whereas Ni and this delta N is also low. So it is not wise to add these very small number, say 10 to the power 6, 10 to the power 7, 8 or 10 to the power 10 with the 10 to the power 16. So ultimately it is in the order of 10 to the power 16, that is N0. So we can write here, this is tau P into N0, this very small. So this we can neglect. These are the small value compared to N0 value. And here also the P0, the minority carrier, is also very small, because N0 is a N-type semiconductor we have considered. So P0 is small. Delta P is okay. This is excess minority carrier concentration. Ni is also very less. So this can be written as, so tau n into delta P. So here you see P0 N0 is equal to Ni square. So you can easily cancel these two terms. Now out of these, here N0 delta P plus P0 delta N. P0 is itself very less because it is N-type semiconductor, and delta N value is multiplied with the P0, so this will be also very less. And the delta P delta N, this product of these two, also small in a low level injection. So ultimately you can get, this is also small. So this becomes N0 into delta P by tau P N0. Because tau n delta P, tau n into delta P is very less compared to the tau P into N0. Because tau n and tau P may be comparable value, but delta P is much less than N0. N0 is the majority carrier concentration. So it can easily be neglected from the denominator. So tau P N0. So this we can write almost equal to, not equal to. So this is equal to delta P by tau P. This is an approximate expression of recombination rate in a N-type semiconductor, N-type silicon, say N-type semiconductor under low level of illumination. Also the delta P delta N product is less, we should write here other explanation also, because why we are neglecting all these terms except this N0 delta P. P0 is very small, P0 is small. So P0 delta N in the numerator is small, delta P delta N is small, tau and delta P already I have mentioned. So ultimately you can get the recombination rate in a N-type semiconductor is almost equal to excess minority divided by minority carrier lifetime. That means there is no relationship with the majority carrier. And in a N-type semiconductor, recombination rate is mainly controlled by the recombination lifetime of minority carrier. So minority carrier lifetime is important for a low doped semiconductor and low level illumination. So the ultimate conclusion is that for low level illumination, recombination rate is governed by minority carrier lifetime, not majority carrier lifetime. That is, majority carrier lifetime has no role in this particular case. So we can write low level illumination case recombination of carriers is mainly determined recombination rate determined by minority carrier lifetime. This is very important. So next, let us consider for a high level illumination. What will happen? Say again we consider a N-type silicon semiconductor, but it is illuminated at a high level of light intensity. Again uniform illumination, that is position dependent variation we are not considering. So N0 and P0 before illumination, the carrier concentration. After illumination, N and P. N is equal to N0 plus delta N. P is equal to P0 plus delta P. And delta N and delta P, they are equal because electron holes are generated in pairs. But unlike the low level illumination, you cannot tell here that the excess carrier, minority carrier delta P is much less than N0, that you cannot tell. That is, here delta P is much less than N0, this is not valid for high level illumination. So let us derive the rate. Pn minus Ni square by tau P into N plus Nt plus tau N P plus Pt. In the similar way, like the earlier case, here also in the numerator we can get the expression, but the N0 and delta P cannot be neglected in this time. In earlier whatever we have neglected that value. So in the numerator part it will be P0 N0 plus, better to write the little expression first, P0 plus delta P, N0 plus delta N minus Ni square, with the same example that Ei is equal to Et, so Ni is equal to Nt. Actually, if the trap state is exactly at the middle, then the maximum rate of recombination is obtained. That's why the assumption of trap state at the middle of the gap, forbidden gap, is a quite natural and is a likely. That's why we have assumed also the trap state is exactly at the middle. So Nt will be Ni. So tau P into N0 plus delta N plus Ni plus tau N P0 plus delta P plus Ni. Again, P0 N0 plus delta P N0 plus P0 delta N plus delta P delta N minus Ni square. P0 N0 and Ni square is cancelled out because P0 N0 is equal to Ni square. Delta P delta N, this also the small product of these two small values compared to other terms, of course, compared to other terms. N0 delta P cannot be neglected now because N0 is a majority carrier concentration and delta P is also sufficiently excess minority carriers are generated. So this product remains. But P0 delta N, though delta N is high here, but P0 itself value is very less because a minority carrier concentration in N type. So this can be taken as a small value cross. So delta P N0 will be the final term in the numerator. And in the denominator, say tau P N0 plus delta N plus Ni. Ni is small compared to the value of N0 value. Delta N is also compared to N0 is less. So this can be written as tau P into N0 plus here the P0 into tau N plus delta P into tau N. So P0 is itself very small because minority carrier concentration, it is can be neglected. Ni can be also neglected. Here also Ni can be neglected. Delta N here cross means is very small plus tau N into delta P. Now this is equal to, now delta P N0 by tau P N0 plus tau N delta P. So further assumption we can do in this way. High level illumination, that means delta P may be comparable to the N0 value. So we can write high level illumination delta P may be comparable to N0, majority carrier concentration before illumination. We can write here the delta P square by tau P N0, that is delta P, N0 is delta P. So if you take the delta P common, it will be tau P plus tau N. So one delta P is cancelled out. So this will be equal to delta P by tau P plus tau N. R. That is the rate. The difference from the earlier case is it was delta P by tau P in case of low level illumination, but here delta P by tau P plus tau N. That means carrier lifetime of minority carriers as well as carrier lifetime of majority carriers both play important role in final recombination rate. But in case of low level illumination, we have seen rate depends only on the minority carrier lifetime. But in case of high level illumination, recombination rate depends both on minority carrier lifetime as well as majority carrier lifetime. Because here, one from the basic sense of physics we can consider in this way, in a low level illumination, excess minority holes are less compared to the majority. So, recombination of holes with the majority electrons will be mainly controlled by the minority carrier lifetime, at how many minority carriers are there, how they are recombined with the electrons. But in case of high level illumination, the excess minority carriers, that is hole, that is comparable to the minority carrier recombination. So both are equal in amount almost. So in that case, it depends on both how the majority carrier will recombine with the minority carriers, or similarly how the minority carriers will recombine with the majority carriers. So that's why the both terms appear. So these are the two cases we have shown. Similarly, for a p silicon under high level and low level illumination, you can start and you can see, you can observe that the same result you can achieve. So ultimately, the rate of recombination depends on the level of illumination. Another type of recombination that we discussed in lecture 19 again, that is surface recombination. And if you remember, in the case of surface recombination, the surface recombination velocity terms came. And this surface recombination model can also be applied to the interface recombination model. In solar cell structure, if you observe, there are so many interfaces between different materials. And you have to consider the recombination at all the interfaces to accurately model the solar cell, or in case of simulation, to get the accurate result, you have to consider recombination at all the interfaces. At the same time, you have to consider the recombination due to bulk. The recombination due to bulk, what I discussed, that is surface SRH recombination, that you have to consider. Along with this surface recombination, you have to consider. And in equation 53 and 55 in lecture 19, we have described or we have derived the recombination velocity expression and also the rate of recombination. This is the surface recombination velocity. And here the surface recombination velocity for electron is coming as a capture cross section, also thermal velocity into NST. But here NST means the defect states per unit area, not per volume like NT. So that's why it is NST. Similarly, SP is equal to sigma p VTP. NST is a surface density of defect states. That means number of defect states per area, per centimeter square or per meter square. Or now, in the same form, if we like to write the equation, we can rewrite the equation 48 again in lecture 19. The recombination rate due to surface states R surface, and the rate is per centimeter square per second. But here you may note R, what I discussed, SRH, that is unit is per centimeter cube per second. But here surface it is per centimeter square per second. Pn minus Ni square, same term, but in denominator it is Sp inverse by n plus n1 plus Sn inverse P plus P1. It was tau P tau n in case of this, but it is Sp is surface recombination velocity. It is dimension is centimeter per second or meter per second. So inverse you have to take. So second per centimeter, then only it gives you the surface recombination rate. Or you can write that is equal to Pn minus n square P into n by Sp inverse n plus Nt plus Sn inverse P plus Pt. And finally, the surface recombination, bulk recombination due to SRH, if there are a bulk recombination due to Auger recombination, due to some other radiative recombination, all you have to consider for accurate modeling of solar cell. And in case of addition of rate of recombination, you can use the formula for simple addition of rates, but lifetime it is inverse, addition of inverse. Say R bulk, the total is R SRH plus R Auger recombination plus R radiative, if there is any radiative recombination. All rates can be added, or 1 by tau effective is 1 by tau SRH plus 1 by tau Auger plus 1 by tau radiative. That is lifetime you have to take inverse then add. So in this case, total bulk recombination rate can be written. But in the bulk recombination rate can be added with the surface recombination rate? No, there is per centimeter square. You have to convert in a characteristic diffusion length. After dividing this rate by a characteristic diffusion length, this becomes the R total, and in that case the total bulk recombination is this, suppose. And another case, say total recombination can be taken as a characteristic diffusion length. I can write here in the box R total is equal to R bulk plus R surface by dl. dl is nothing but characteristic diffusion length of carriers, some nanometer range. That means near the surface, what is the diffusion length? There is the distance from the surface within which carriers may reach to the surface for recombination. This is the characteristic diffusion length. But dividing R surface by dl gives you the rate per centimeter cube per second. Then you can add this thing to get the total. So these are the total recombination modules or models for solar cell or any other devices. We will use recombinations for each layers and interfaces when we do simulation of solar cell to get the accurate result. So in this lecture we have discussed Gaussian distributed near mid-gap states, which are mainly responsible for carrier recombination. We have seen for low level illumination, rate of recombination mainly depends on minority carrier lifetime, whereas for high level illumination, rate of recombination depends on minority as well as majority carrier lifetime. These are the references you can follow for this lecture. Thank you.